Hi folks, and welcome back to Math with Captain Rod. I'm making this video here to help provide examples of how to sketch graphs of polynomials. So what we're going to do is we're going to sketch a graph of this animal here, this h of x equals x minus 1 the quantity cubed times x plus 3 the quantity cubed. Alright, so before we get going, let's chat about how this thing is going to behave long term, the LTB, long-term behavior of this function. The highest order here in this part of the equation here is x to the third, and the highest order here is x squared. So ultimately, if you multiply this out, this thing is going to equal x to the fifth plus a bunch of stuff here, where the bunch of stuff will be like x to the fourth, x squared, etc. This is the most important term when you're looking at long-term behavior. Now, x to the fifth is an odd function. When x gets really large, this goes to plus infinity. So, you know, what's happening kind of close to the 0, 0 here, we're going to talk about more detail, but ultimately this function has to go this way and this way, and that's because of the x to the fifth. When x goes to plus infinity, this will go to plus infinity, and when x goes to minus infinity, this value will go to minus infinity. Right? So ultimately this function has to do, come up kind of like this, and then it's probably going to do some stuff in here, and then ultimately it has to leave kind of looking like that. And we'll take a look at the more details here now. All right, so this thing has a 0 at x equals 1. You'll notice if you put x equals 1 in, we get a 0 here. And the multiplicity of that root is third order. So we know it goes through the point 1, 0. Now the 3 is important because that's an odd number, and that means that function changes sign, SIGN, when it goes through this intercept. So that means it's got to look either like this or possibly like this, and we'll fill out details here in a minute. This function also goes or has a 0 at negative 3, right? Because negative 3 would make this guy a 0, so 1, 2, 3. Now the multiplicity of this root is 2. This quantity is positive on both sides of this thing. So roots like this that don't change sign, they look either like this or like this. Anytime you have an even multiplicity here, that'll be the case. All right, some other things to chat about is maybe let's get the y-intercept here. That's always a great thing to put on graphs. It's typically a lot of times pretty easy to get. So if we set x equal to 0, right, and we calculate h of 0 is going to be, let's see, 0. That's going to give us a negative 1 cubed is negative 1. We put a 0 here. Plus 3 is 3 squared is 9. So this goes through the point 0, 9. So let's put that on there as 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So I'm just thinking about this graph here a little bit. All right, so now kind of putting things together. The 1 had multiplicity of 3. Oh, now I know why I'm confused. I'm sorry. That's 0, negative 9, not positive 9. Oops, that's down here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I was just staring at that going, that graph doesn't look consistent with what I've been telling you folks. All right, so now look, that's enough to maybe kind of sketch it. Some points over here or over here would help, but again, this is just supposed to be a rough sketch. So remember that this root's coming from this, from this one, has even multiplicity. So sketching this is going to look something like this. Even roots with even multiplicity do not change sign, like go from minus to plus when you go across them. Wow, that thing, we know it does. We know it goes through here somehow, and then here, and I could plot a few more points to fill in some detail. This is not necessarily a turning point on the graph. Like what I'm saying is this point is not necessarily here. I think looking at it, it actually is, to tell you the truth. That does end up being a turning point, and the way that I'm calculating that is beyond the scope of the course, but I'm just going to call that good. Here's our long-term behavior. This goes up and right. When x goes far to the left, this goes down. We have roots in their correct places, the intercept, and I'm just going to call that good here. This is just meant to be a rough sketch, and I think that probably is a reasonable approximate sketch of that function. Have a great day.